So we are in the physical chemistry class. The goal of the class is to describe properties and of chemicals, molecules, and materials, and maybe some reactions. And in order to do so, we need to get properties of electrons, which are essential part of all atoms and molecules. And in order to do this, we need to follow their wavy nature. So we did some steps on considering traveling wave equation, then accumulation of phase along the trajectory, which is called action, right? And then by making derivative of this philosophical wave function, we got an equation, the differential equation, that you fabricate wave functions in any circumstances if we formulate, if we set up the energy operator correctly. So last time we did derive time differential integral equation, and today the goal is to get the simplified version, so-called time independent integral equation. I did promise you that it has like 5 symbols instead of 12. And in narrow sense, any quantum theory and physical chemistry can, in very narrow sense, can be considered like a set of mathematical tricks to solve time independent Schrödinger equation. So it's a narrow sense. I do not want you to think so, but as a central point, it's possible. So here are the postulates that you have, and I just select this one because it is the shortest that one can fit on one screen, but you're welcome to browse around, and if you bring some controversy and mention it, it's fine, because foundations of quantum theory are more controversial. So you're welcome to browse through books or Wikipedia or other sources. To my understanding, based on your votes, here is the schedule. If you do 5 minutes per person, you will fit in 40 minutes. It never happens. It may take a little longer for introductory work, for processing forward, backwards, and asking questions, but approximately it is what we will be doing next coming Friday. And please send PDFs, PowerPoints of your presentations by Thursday, 11:59, like midnight. The reason is if everyone will come with a memory stick or log in, log out, we will lose tons of time, and those who need to visit next class will be late. So I will upload everything to the central podium, and then we will quickly switch slides. And also I cannot do much at the midnight, but I will throw a glance and tell if there is something very wrong that you can correct at the last minute. Okay, so what last time we together derived this equation, which means the psi wave function is probability amplitude that we also interpreted. If you take square, it will be probability to find out a specific point of space and time. This is total energy, one constant imaginary unit, time derivative. And this is the thing that led Erwin Schrödinger for being popular, because it's efficient formulation of all philosophical ideas that we discussed in one equation. And then we also did a concept of commutation. So in order to formulate total energy, the symbol H, Hamiltonian operator, one needs to replace whatever we used for the energy in classical mechanics, like kinetic energy through momentum or potential, into quantum operators. And quantum operators are formulated as often as differential equations. So the swapping of the order of operators is not for free. One is getting either penalty or benefit for it, but changing order is not for free. And here is an example. We are going through applying derivative and linear function with direct and reverse order to the function. We saw that just by rules of derivatives, it's once they do not commute. Okay, the last thing that I missed on the last meeting, but it last but not least, and one of you will present it on Friday. So this equation, I would say it is a bridge between abstract concepts in quantum theory and the real world. So if you are doing research in the web, or if you characterize materials with spectral photonic or NMR machine or something that gives you data characterizing the materials, you typically get numbers, and people call them observable. If I measure how intensely this molecule emits light at given wavelengths, so it is a number it can be measured. In quantum theory, one can set up combination of basic variables like that determine this observable. And here is what this equation means. If you set up the combination of differential operators, combination of that will correspond, will define the observable that you measure, and then this one is typically differential operator, and then you multiply it from the left and the right by the wave function and integrate, then you will obtain the expected outcome of the measurement. If the system, if the electron in our molecule, or more narrowly or broadly, ions can be also part of the wave function. If the wave function of the molecule you're describing is in this state psi, and because of being lazy, I'm not writing like brackets and arguments. But if it is in this function psi, then the result of measuring observable A will be, in average, the thing that one is getting by practicing this equation. Make sense? So we are computing wave function in order to predict observables that are measured on the experiment. And this is the bridge. We are not, it's not like abstract exercise for the brain. We will have predictive power to interpret or predict outcome of experiments in the real life. And here is one of the table that one of you will probably show and focus our attention once again. So it's how they, this basic variables, basic properties like momentum, position, angular momentum are converted into differential operators. And right now we are just throwing a glance. As we go through the course, we will slowly but surely focus on each of them. And you'll see that it is not so complicated. Maybe you already recognize it, that it's not more complicated than second derivative. So what are we going to get today? So if you feel comfortable with this slide, this stuff that is written here, you can disconnect from Zoom or stand up and leave the room. So there will be nothing in addition to this. So here is our old friend, here is our new friend. And if I skip the indices and arguments, then number of symbols will be 1, 2, 3, 4, 5. So we need to get acquainted with this equation, which is called time independent Schrödinger equation, because there is no time there, and get some ideas where it comes from and what does it mean and when we can get benefit of it. So this one is total energy. This one is wave function which does not have time, right? So it's time independent wave function. Here, this wave function again, And here is the so-called eigenvalue. And if you were looking on the quote from the Schrodinger's preface, it was a translation from German to English in 20s. They translated as proper value, because there is a property of wave function, and these numbers are eigenvalues are property of the state of momentum. So we'll go through it once several times, and do not worry if it looks a little counterintuitive or surprising. If you are, I heard part of your communications to each other, some of you are in the differential equation class, right? So if instead of this h, you put some derivatives, first, second, this is a known function, this is a known function, this is a known constant. Then such class of differential equations may have eigenvalue problem, may have more than one solution. Right? If you solve 2x equals 1, there is one solution. But if instead of numbers you have functions in differential operations, there will be several solutions. So for right now we are too abstract. Later on, for the whole class, we will put specific thing instead of this h. So for equation of this class, there are several functions, set of functions that satisfy this equation, and a set of these eigenvalues that satisfy this equation. And they are in correlation. Like for solution 1, it corresponds to this proper value 1. For solution 2, corresponds to eigenvalue 2. Do not worry, we will go through it a dozen times at least. And another thing that if these eigenstate wave functions are good in mathematical sense, if they were found in a correct way, they will be normalized and orthogonal. So if one multiplies functions with non-coinciding indices, one will get either 0 or 0 if they do not coincide, 1 if it is the same function. Okay, so I'm going to do nothing but slowly approach to the slide once again that I plan to show in the last minute before we depart. Let me check if anyone on the Zoom has questions. Yes, though it doesn't go through screen share. Yeah, I'll make a little experiment. I'll see how recording's seen, and maybe we'll return to sharing again. Thank you, August. Okay, let's do a little exercise. So I can quickly go through slides. It will be like 5 minutes, but maybe it will not leave a trace in our memory. So if we do have this Schrödinger equation, and we consider wave function as a product of time-independent part, which sometimes one can call capital X, times time-dependent part, which one sometimes call T, capital T. Let's just plug in this stuff here and there and see what happens. So if we plug into a product under this differential operator, we will get time derivative of the function that depends only. You can probably do it quicker than I. Time derivative of the function depends only on position times dependence on time plus function that depends on position and time derivative of the thing that depends on time. So since we do not have explicit time here, right, this term will be 0. Make sense? And here is just a little better calligraphy. So this term stays, this term departs. Now the next step. Please, as we go through the course, I will learn there is an opportunity to be very interactive and focus camera, like class instructor. I don't know if you can forward to it or you're against. How do you solve linear differential equations with constant coefficients? Huh? You're not solving them.
Separation of variables?
Okay, it is if there is more than one variable. And if there is more than one variable, and you know sure that equation is linear, there is no product of independent, there is no powers of independent variable, there is no product of independent variable and derivative. There are only derivatives acting on the unknown function.
Oh, you could just use Laplace.
You use what?
Laplace transforms. If it's a linear differential equation.
Exactly, yes, I'm happy to hear it. And Laplace means that Laplace transform and Fourier transform means that you assume that function has exponential form and you are looking forward to expansion coefficients in front of it, right? And you're solving equation for expansion coefficients.
Yep. Mm-hmm.
Is it clear or needs more comments? Probably it does need more comments. So why do we love exponential function? Oh, you hate it.
Easy to solve.
Huh?
Easy to solve.
Because
Quadratic formula.
there are benefits. I've heard suggestion from a fellow instructor what to tell in these circumstances. A joke, and I will reproduce it. I do not consider it super funny, but it was a suggestion. So two crazy mathematicians were placed in the hospital for crazy people. And they are chasing each other and threatening each other when doctors are not looking at them. And one is telling, I will differentiate you. And he answered, I don't care, I'm exponential. My fellow instructor told that the class should laugh at this point. So I told that probably not, but the idea is that what is derivative of exponential? You may answer right now. You don't, okay.
You can just say use the exponential.
If you do, yeah, equals to just e to the power x.
E to the power of x. It's just e to the x.
Yes. So what happens to exponential if you differentiate it?
Not much.
Right. So it stays the same function. It is why we love exponentials. It is why we put them everywhere. So if the differential equation, and if you take second, third derivative, it will be still exponential. If you will set up just agreement with yourself that my solution of differential equation will have the form of exponential, maybe with some coefficient in front, maybe it will be not x, but like alpha x, but then by applying derivatives first, second, blah, 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 you will get the same function. And this exponential will for sure satisfy linear differential equation with constant coefficients. I'm not a mathematician, so I do not know if there is a theorem, but it is a very good rule of thumb. If the differential equation has only linear, only, how to say, time-independent coefficients and only derivatives, then solution will be exponential or summation of exponentials. And through this rule of thumb, we can immediately practice, we can apply it to here. So there is a derivative of this time-dependent thing. So why don't we assume that this t of t is just e to the power ct, exponential with unknown coefficient in front. Then ddt of t will be c e c t, right? And then I'm going to glance back on the previous slide because my memory is not perfect. So we have derivative of t times time e independent part. So wherever, so we will have c e c t times x equals minus I h bar energy operator e c t times x. So we do have, so instead of this unknown dependence of time, we did plug in this exponential. Through derivative, we just get a coefficient up front. And now we do have exponentials on the left and right part of the equation, right? And they are not any more quantum operators. They're just regular functions that we have freedom to cancel, right? And as a price for it, we are going to get equation only for this function x capital. And the only memories about that something was related to time will be this unknown coefficient c. Make sense? Here is just a little better calligraphy if you hate my handwriting. So plugging in this e to the power ct here and there. And then having this coefficient up front, and then we can cancel this exponential e to the power ct. Okay. Cancel. And next thing, just to follow the common notation of the rest of the world, instead of x capital, typically people use Greek letter phi if it is time independent. If it is a wave function that depends only on position. So it's a previous version of slide that is not updated. Okay, but all things are here. So we do have c phi of x equals minus I h bar h phi of x. Now we can multiply left and right by multiply by h bar divided by I. So c h I phi of x equals h phi of x. So just let's call for simplicity this as letter E, but it is more than that. one can show the dimensions that C multiplied by time will be dimensionless, then C is 1 over time. So if 1 over time multiplied by Planck constant will be dimensions of energy. So this will be energy. This is set of differential operators, and here is unknown function. So we arrive to the time independent Schrödinger equation. So it is an equation for a function, but the dependence on time is so trivial that we just skip it. It will be always exponential oscillations, right? And this, if we can set up that C equals minus IE divided by H bar, right? So if the energy is real, then the coefficient C will be imaginary, and this T thing, the E minus I H bar energy times T. So it will be just imaginary exponential that will accumulate phase in time, and whatever energies we get out of this time independent Schrödinger equation, we will accumulate this phase quicker or slower, but it is kind of trivial. And it in some sense relates to what August suggested about Laplace transform. So that one can assume that solution has exponential form. So and this equation has more than one solution. So by solving it, and we will look for the ways to solve it, but this form of equations typically has, you solve and find, same as polynomial equation, algebraic. If you type like C sub n x power n plus C2 x to the power n minus 1, like quadratic equation but to infinite power. This equation has several roots, right? Very similar. This one also has several roots. Those are roots, and those are functions that correspond. Okay, what else? So the word eigenfunction and eigenvalue corresponds from German. Eigen means like own, proper. And we are almost done, but I want to show one more little thing. Yeah, oh yeah, we do have time. I think a slide with a little better calligraphy. So if I would be sitting in the class, I may develop an irritation towards the class and the instructor because the material is too abstract. It is natural wish to have some more practical examples. And the rest of the class will be big practical example. But now we can do very, very little one that one can fit into a few minutes. So we are going to look onto solution of this type of equation, eigenvalue problem. But for the energy operator, it will be too much. We will not fit into a couple of minutes. We will select, it will be different operator. And sometimes solving problem directly is challenging in math and differential equations. If we do not need to solve, if we need just to make an example, let's set a problem of reverse engineering. Let's look at a given function and find, as we did before, which equation it will satisfy, which eigenvalue problem it will satisfy. Like if you know the function, what will be this proper value, eigenvalue, and what will be the differential equations that may generate this function. So for this example, I will select the this one. So exponential to the power IPX or H bar. So why? So it's kind of mathematical experiment. Why I'm offering all of us to follow it? Because quantum theory is laid on the foundation of Bohr theory, which is not correct today, but it was good logical step. And in this Bohr theory, one is looking onto angular momentum. Like only with those orbits are permitted, which have certain angular momentum, which have this integer number of nodes and lobes, and the action has discrete values along the path. And this angular momentum on one hand, and now you are well-educated experts in this philosophy of quantum theory, the action, which nature tries to minimize, can be composed as product of position and momentum. So if you divide it by this dimension constant, then it will be accumulation of phase along a trajectory, right? Maybe in this example, if you do it one dimension, it will be just accumulation of phase along a linear trajectory for continuous motion with constant velocity. So likely, looking at this equation, it may mean that some distributed wave is traveling in a certain direction. But now let's convert this solution, this function, back into equation and look what will be eigenvalue, what will be like. Let's try to make connection between this stuff and the eigenvalue problem. So, the thought number one. You already probably found a pattern we are doing here. We're just taking derivatives of things. So if you take derivative of this function, I'm not doing it because it's probably quite simple. Taking derivative of exponential, we get everything except of independent variable open up to the front, right? Which is momentum, imaginary unit, Planck constant. Now let's compare first and second line. Time derivative, not time, derivative over space and momentum divided by Planck constant have something in common. If we are permitted to cancel the function, we will have the relation that derivative over space is equal to momentum over Planck constant. Let me check if anyone on the Zoom wants to object it. Are there any objections or questions from August, Adam, or Kennedy? No objections. Thank you, August. Okay. Continue. So if you cancel this function, we will have the derivative equals to this one. And if you multiply everything by Planck constant and divide by imaginary unit, we will have this relation. So momentum, we just process this equation. So momentum can be expressed as derivative over space multiplied by this minus imaginary unit h bar. Why there is minus here? We need to comment on this. So here we divide left and right by I, and here it is again back in the nominator. So how do I place imaginary unit from denominator to numerator?
So you can take I, you can times it by I over I, and then you'll get negative I.
Thank you, August. Does this make sense? So it's definition of imaginary unit. It is the number that being squared gives -1. Therefore, so it doesn't matter which form we take, but it's like some people hate denominators and try to put everything in line. But then as a price one put -sign. So, and in the table of conversion of classical variables to quantum operators, it is line number 1 or maybe line number 2. So momentum is replaced by derivative over space. Make sense? Okay. Okay, this is just without interpretation. If we draw this infinite oscillating thing, if you try to draw this oscillating exponential, the momentum defines how dense or sparse fringes are. And large momentum means dense fringes. Small momentum means sparse fringes. And if we carefully follow definition of the wavelengths as the distance between two maxima of the function, then one can interpret the stuff in the exponential as 2 pi divided by lambda, divided by the wavelengths. So in some sense, for the plane wave, the momentum is inversely proportional to the wavelengths. It is not the wavelengths that we are speaking in spectroscopy for the light. It is wavelengths of electrons. No objections? Okay. And now just let's summarize this little experiment. So on one hand, we do have the momentum as operator. So if you put this momentum with little head in front of this function, we will practice the derivative and get the p without head that defines the wavelengths. So this p here and there do have a different meaning. The p with head means differential operator, and p without head means like actual property of the given function. It's just a number. So one can say that it is observable. It's actual value of momentum. Number and operator. And here is the correct statement that we did prove, or just there is nothing to prove. It's just one derivative. But here is how one can interpret. If this exponential with either dense or sparse fringes is called phi of x, then this p with head will be operator, differential operator. P without head will be eigenvalue, and phi will be unknown function. Well, it is known for us, but we can wipe off everything and keep only these colorful boxes. So if someone places this equation, differential equation in front of us, with p is defined as this differential operator, the solution of this equation will be this exponential. So we didn't solve, we took solution and then reconstructed the equation, but now we see the consequence. So we can, by looking at the equation, we can assume that it will be set here, the values of momentum can be any. They can be continuously incremented. There is no discretization, there is no restriction. But as soon as we set up eigenvalue, you can find eigenfunction by plugging this p into here. Practical problems that we will be solving later will look a little bit different, but the idea of operator function eigenvalue will be the same. And by the way, the stuff is called plane wave. Okay, done. Looking forward to see your slides and your faces on Friday. So please check if your cameras are working. I'm finishing the